Hi, my name is Jonathan Howe. I'd like to talk to you about some work we're doing on multi-agent autonomy navigation. This is collaborative work of the Aerospace Controls Laboratory, working with Kaveh, Kazar, Matthew, Yulin, and Parker. So in terms of multi-robot systems, of course, there's many challenges that have to be addressed. On the coordination side, you have to investigate whether or not we can navigate without requiring external positioning, and how to ensure that the collaboration of the local decisions lead to achieving the global objectives. In terms of the task assignment, there's a question of whether or not we can actually figure out which agents are doing which tasks. We'd like to be able to compute that in a distributed and computationally efficient manner. And in terms of resource constraints, we'd like to make sure that the algorithms are resource aware, so we take into account the communication, the computation, and the power requirements for the different algorithms that are going to be implemented. There's two bodies of work I'd like to talk to you about today. The first being the distributed pipeline for scalable deconflicted formation flying, and there's both a paper and software available if you'd like to take a look. And I probably don't need to spend much time motivating multi-vehicle formations for this audience, but there's a lot of work going on in this area, both on the entertainment side with the UAV swarms doing light shows and dancing robots, of course. And on the military, there's both the Perdix launch of UAVs coming off the F-18s, and the swarming, and then the offset program currently running in DARPA, which is also looking at how to use swarming vehicles to do situational awareness investigation across military domains. So there's a lot of interesting applications, and what we'd like to look at is a quick deployment of UAV swarms to achieve information in environments with no infrastructure. Part of the motivation for that is that sometimes if you're flying indoors, there can be a navigation failure due to just the lack of GPS even being there. But even when you're flying outside, there can be an inadvertent jamming from things like a power station, and then you just have the UAV lose control and crash. So what we'd like to be able to do is to do a UAV swarm, but without relying on an external sensing infrastructure. I would also like this to be a decentralized execution, so we have scalability to a large number of vehicles without creating a communication choke point at the base station. What this is going to require is that we have a distributed control and decision-making system to reach the formation without colliding and avoiding gridlocks at the same time. And what it's also going to be able to do is to make sure that we address the local sensing, which tends to lead to a situation where the reference frames of the UAVs may not be aligned. And that's something we have to account for in the design process. So there's lots of prior work in this area. The Automatica paper in 2015 alone lists 130 formation control papers, and there's lots of different axes that one tends to think about the differentiation between the work, but three primary ones are the control and decision making, whether it's centralized or distributed, communication, whether it's frequent or sporadic, and the sensing, whether or not it's global or local. In this work, we're operating up here in the top right. And what we'd like to be able to do is to implement a distributed control so there's no single point of failure. The sporadic lightweight communication, so there's no saturating the communication channel and the result is scalable. And that furthermore, we're using local onboard sensing, which would then work in a GPS denied environment. And furthermore, it's going to be, the techniques will be robust to the misaligned local frames that I talked about before. And we'll come back to this picture in a second. So the setup then is that there is a base station, but all it's doing is dispatching the desired, or computing a desired formation and dispatching it to the agents. But this can be done at priority. And so there's very little communication required in this link right here. What's occurring in the vehicles themselves is a VIO and pose update, which is a shared activity across the team, a task assignment, which is also shared, and formation control, collision avoidance, and some of the lower level control as well. But what's given to the team then is a desired formation coordinates are in an arbitrary frame. It's really just a description of where the vehicles are with respect to each other, but not necessarily specific points in space. And that at that time, each UAV is assigned a specific role or a point in that formation, but given as a result of us running a task assignment algorithm in real time, that role can actually be reassigned in real time. So again, thinking about this picture, there are different assumptions that people typically make in terms of these local frames. And the standard one is to just use a global frame where all the vehicles are working off the same coordinate system. Another then is local, but basically not what you're then doing is having all the frames be aligned, but not necessarily in the same direction relative to a global frame. In this work, though, we're not spending the communication effort to actually ensure that consistency exists, and we'll just work in a situation where the vehicles, as a result of obtaining local sensing information or running a local VIO algorithm, may actually have misaligned frames, and we will compensate for that in the design process of the control algorithm itself. So again, the UAVs will have non-aligned local frames due to this local sensing, and that furthermore, they can only communicate with few, not all other UAVs in the neighborhood. And the control strategy that will be based on that local and limited information, but what will give then a guarantee that the formation is globally achieved. Now, the actual approach that this is done is a calculation where each UAV, say number one here, figures out where the other UAV is in that coordinate frame, and then using the gains from the formation control algorithm, it actually decides how to both rotate and scale each of those directionalities to the other UAVs, as it does here with UAV 2. It then finds that vector, rotates it, and scales it, does it the same thing for UAV 3. The resulting combination of those two vectors then gives UAV 1 a resulting velocity command, which through some assumptions about what the motion model is for that UAV, we can then convert into a resulting control command that actually has to be executed. So that sounds great, but to do that, we need to know what these formation gains are, and those can be computed using a semi-definite program. And this is the formulation of that program that's given here, and it's written up in the paper as well. The difficulty with that is the off-the-shelf STP solvers are not scalable and only work up to about 20 UAVs. And once you go above that, as shown down here with some of the numbers in this table, the CVX, when we're running it, just basically ends up in an out-of-memory situation. So what we created instead was a customized solver to leverage the problem structure using ADMM as the solving technique, and is just a schematic of the steps used in running that algorithm. And the result then is we can run up to not just 20 UAVs, but actually go up to about 100 UAVs and compute that solution in about 12 seconds. And again, this is something that can be computed offline. It's basically just something that's deciding what type of formation we'd like the UAVs to execute. It can be done a priori. And then given to the UAVs before the mission begins. So these numbers are not large, but we can actually run the calculation, which we could not do if we're using a centralized solver. Now, there is a situation where you could actually distribute that ADMM solver across the UAVs if you wanted to. It would result in higher communication costs, so it's something that has to be considered. But the key takeaway from this is that we have a design technique. It is centralized, but the execution, once we have the formation gains, is completely distributed, and there's very limited onboard computation required using the technique that I described on the previous slide. So that sounds great, but the problem is, how do we avoid collisions at the same time? Because now we have a bunch of UAVs, and they're probably flying across to different points and possibly colliding with each other. But it turns out that we can prove formation convergence is not affected by either a positive scaling of the control vector. So if this is the resulting, you can scale it up or down, or you could in fact rotate it by as much as plus or minus 90 degrees as shown here. So that gives us a lot of freedom, a situation where maybe this UAV realizes it's going to collide with another, and what we can do is put a sphere around of safety around each of the other UAVs, and then use that to determine how to modify or create a deviation in the resulting control command that this UAV would actually be executing, and that would then give us some safety on the collision avoidance. So that sounds great, but of course there are situations where you might end up in a gridlock, as shown by the two cases down at the bottom. This one where the situation where the safety, the situation requires that we make a deviation that's larger than the plus or minus 90 degrees that we talked about. And this one here, there is just no situation or no change in the resulting command other than scaling down and going to 0 that would actually be beneficial. And so there's a situation now where we have a gridlock, and what we have to do is come up with a different solution, and that's where what we actually do is reassign the UAVs to different points in the formation. So the second step then in resolving the safety situation is to actually have a situation where we have the UAVs where they might previously had been assigned to one point in the desired formation. We now put it up for auction that they would choose a different location or different point in that in the desired formation instead. But again, the challenges here is that each of the UAVs is working on a non-aligned local frame, and so the UAVs must agree on the alignment of the desired formation. And again, they're not agreeing on the alignment of their own frames. What they're agreeing on is what is the alignment of the desired formation. And again, that's in a arbitrary frame. It's just a description of where the UAVs would actually be relative to each other. And the other problem, of course, is that we can only communicate, or each UAV can only communicate to its neighbors, and so there's no central task assignment authority available. So the approach then for the task assignment consists of two steps. Step one is an alignment step, and what we're doing here is actually aligning the best orientation of the desired formation to where the UAVs currently are, and that involves both a rotation and translation of that desired formation as we essentially wrap it around the UAVs in the current locations. And then the next step is, once we've decided how best to line up the desired formation, we then assign each of the UAVs a point in that formation, which hopefully is a new point, and then we're in a situation where we would then have hopefully resolved the gridlock situation discussed on the previous page. The algorithm used for doing this is CBAA, which is a simpler variant of the CBBA you might have heard me talk about before, based on a paper we published in TRO in 2009. And one of the highlights of this paper is that it does not require that the agents have similar situational awareness while they're making the decisions about the tasking. And that's, as you can imagine, a situation that exists here because the frames are misaligned, and the agents themselves may not have this similar or consistent knowledge about the actual cost of going to a different point within the desired formation. But none of that matters, and you can actually show that the algorithm will converge. And again, that's sort of shown here in the cartoon example, where the key thing to highlight on this slide is just a situation where, in this case, if you think about it from agent A's perspective, and it's thinking about alignment of the desired formation in its own coordinate frame, and thinking then about the cost of where it might go and which location in that frame would be, in that desired formation, would be preferential for it. And then there's a parallel calculation done on board each of the UAVs, and this is just cartoon. This cartoon is just showing what would UAV D's perspective be on the solution, and it too will go through into a calculation of what it thinks the desired locations are for itself in that formation. And then each of the UAVs is bidding, and it goes through a process that's described in the paper on how the bidding process actually works. And you end up in a situation where, although the UAVs have very different perspectives on where the desired formation may be relative to their own coordinate frame, you end up with a conflict-free assignment of the UAVs to the formation points, which is the key thing that we need out of this. And so again, what we have here is a situation where we have the gains that tell us how to actually execute how each of the UAVs would actually achieve the desired point within the formation. We have a collision avoidance algorithm to make sure that they don't collide. And if they end up in a gridlock, we have a reassignment capability to give them a new task within the desired formation. And then we're in a situation where that can hopefully resolve the gridlock. So in terms of an experiment, the kind of thing you might see here is on the left, what you see is a picture where the desired velocity and position of the UAVs is shown. And on the right, we're flying the UAVs around in the high bay using the VIO software, tracking we'll figure out where they are relative to the ground. And in each case, we have a situation where the desired velocity is sort of highlighted here. And you'll see situations where gridlock's occurring. We're sort of intentionally creating it here. But through the process of reassigning the UAVs different tasks within the formation, and again, possibly realigning the formation at the same time, we now have a situation where we can actually overcome the gridlock and basically just have UAVs go to different points in the formation than they were intending to go to originally. So that's one set of experiments. And the key part, and this is just showing some more, there's a sort of a three-dimensional type of formation that we're trying to accomplish. And again, doing it with and without assignment at the top and with assignment at the bottom. And as before, without the reassignment, we have a gridlock situation where the UAVs end up sort of stuck here and don't know how to move around. And that's consistent with the fact that without reassignment, if we were doing about 60 UAVs as we're flying here, the success rate's as low as 59%. Whereas with assignment, it gets up to around 100%. And when we scale it up in simulation, about 30 UAVs, success rate is a little bit lower, 97%, but still a lot higher than happens without the assignment. And again, a lot of this has to do with the fact that we are running a suboptimal auction algorithm here that's only and part of the key part of that suboptimality is a result of the local information, or the only having local information that's available in each of the UAVs. And that could be resolved, but at a communication cost in terms of actually trying to ensure that the vehicles have more consistent local information. So we've scaled this up to a much larger situations. This is sim with 100 UAVs to demonstrate that scalability, and that's part of the software package I mentioned earlier. And using consumer-grade Wi-Fi connectivity, we expect this would be able to scale up to about 800 UAVs as well. And in this case, they're just spelling out MIT-ACL. So the second body of work I want to talk about is the resource-aware collaborative loop closure detection with provable performance guarantees. And again, there's a couple of papers here that you might be interested in taking a look at. The problem statement in this case is sort of shown as a cartoon on the right here. We have, say, the red UAV wandering through a forest and the yellow UAV wandering through a forest. In this situation, they never actually see each other, but they end up seeing similar things. And in fact, the red's flying down this path this way, the yellow's flying down that path that way, and they end up having an overlap in the features that they were seeing. And ideally, you'd be in a situation where what we would be able to do is, in this sort of GPS-denied forest setup, have the UAV share features between themselves and then come up with a better solution for their navigation sort of estimate by working together. So the key part then is that each agent has made several observations, and what they're trying to do is collaboratively find the inter-agent matches between these observation pairs and find situations where from those matches they can then improve the navigation solution. But the challenge is that this is a pretty resource-intensive process, both in terms of communication bandwidth, the battery, and the compute power required. And that there are centralized solutions that exist, but they tend to be pretty inefficient and they're not robust, and they require that connectivity in terms of getting all the information to one place. And the standard solution then as an alternative is just our broadcast all, where everyone just throws all the information out there and says, this is what I saw, can you find any matches? Which is grossly inefficient in terms of utilization of these resources we listed up here. So the research questions we've been looking at then are optimal communication planning. And so again, this isn't necessarily path planning, but this is thinking about who must share what with whom. And so it's thinking about a policy, but that policy has to do with communication. And of course, there's resource awareness that we're embedding in all this, which is how to optimally focus the limited resources that we do have to maximize the performance, which is what we think about here in terms of navigation itself. So again, there's two parts of this. One is step one, which is some exchange of very lightweight metadata, which is sort of an indication in a summary format of places where I've been and types of things that loop closures that we might be able to make. And then there's the exchange of data, which can be much more intensive in both terms of both communication, and then the processing of that data is more intensive in terms of computation. So after step one, the robots then form as an exchange graph, cartoon shown over here with 3 robots, where we have vertices, which is the things they saw, and then the edges here then are potential inter-robot loop closures. So if they think they saw the same things, this is a potential loop closure. And so what we're highlighting here is a situation where there are there's 3 things they saw and a bunch of different loop closures that could possibly be formed. And what we're looking for then is an exchange policy, which is thinking about what observations should we share or not share between these robots. Okay. So what we're looking for then, and the first step is to develop a lossless optimal data exchange problem, which is sort of sets out everything and says, this is, in an ideal situation, this is what we'd like to be able to do. And so what we're thinking about is total data transmission. So we're thinking about, the different robots have seen different things. And so we want to be sure that we're careful in terms of what's actually the total amount that's being exchanged. And then fairness in the induced division of labor. And so again, anytime someone shares something with you, there's a required computational effort required. And we don't want to have a situation where everything gets dumped on one robot, and that robot then has to spend an inordinate amount of computational effort simply to do that computation. And when we could have ideally shared that computational effort around. So we're looking at a minimization of a combination of those two things. And in this sort of optimal problem, we're thinking about subject to the constraint that all potential loop closures are verified. And of course, this isn't necessarily going to be realistic, but we'll start off here for now, okay? And so of course, to verify a potential loop closure, at least one of the robots is going to have to share its observations, okay? So that's a given. And the result of this problem can be cast as a minimum weighted vertex cover problem on that exchange graph. And in the 2-robot case, we know that can be solved optimally in polynomial time via standard techniques such as LP relaxation. But the general case is way harder. It's in fact NP hard. And so what we've developed is an approximate solution via the LP relaxation and rounding, and shown that it's a 2-opt algorithm. One of the interesting things that comes out of this work is a theorem that shows the necessary and sufficient conditions for a monologue to occur, which is essentially a one-way exchange, very much like this presentation. But we show the conditions for that monologue to be optimal in the 2-robot case. And so this is often used as an approximation where, again, one robot is dumping all the information on another. And so while that's typically used, we actually give the conditions to show when it's a good thing to be doing. And the implication of that is that it's not always a good thing to be doing, and that two-way exchange would in fact be better in many cases. Now, of course, that's the optimal data exchange problem, but we typically have a budget that we have to be thinking about, and the budgets are going to be in the form of both communication and also in terms of computational effort. And so what we're going to be thinking about then is the same exchange graph that we had. We're going to have an allocated budget in terms of computation and communication, and then we'll have an objective that we'll have to pick. We put these three pieces together into the creation of this budgeted data exchange problem, which is then going to result in a policy thinking about what we should share and a policy that's thinking about what we should actually go about verifying. So the new problem then is, as I said, is thinking about what to share, which is a subset of the observations will be shared, and then what to verify, which is a subset of the potential loop closures would actually then be verified. So again, going back to the cartoon we talked about before, where there are a bunch of potential loop closures, and we have all of them shown here, but some of them being dashed out. And when those are the ones we've decided we're not going to verify through this algorithm. And then, but the blue ones are the ones that we will, and then these are the pieces of data that we will exchange. There were a bunch of options that existed, but those are the ones that we're going to be limited to. So again, the formulation of the problem here is a little bit different than before, because now we're thinking about, we have a utility, which would be some objective function subject to the constraints on computation and communication that's constrained in the problem formulation. There's discussion down here in the recent IJRR paper. Different kinds of utility in terms of the objective that we will accomplish in terms of exchanging this data. Some are thinking about the expected number of true loop closures, which turns out to be a monotone modular. Others are thinking about the optimality criterion, which turns out to be monotone submodular. And others are thinking about tree connectivity, which turns out also to be monotone submodular. So again, we have some that are modular, some that are submodular, and we get different performance guarantees as a result. Again, as before, the constraint is that to verify a potential loop closure, at least one of the robots must share its observations. And the communication then is going to exchange at most B observations. So in this case, B is 2, this one and this one, these two get exchanged. And the computation then is that we're going to make a decision that will verify at most K potential loop closures. In this case, it's 3, 1, 2, 3. Okay. And as indicated here, take a look at the paper for additional models on capturing heterogeneity and observations in other resource budgets as well. Okay. So again, much harder problem, and in fact, this is NP hard in general. And there are ad hoc algorithms you can create, but in our experience, they tend to perform arbitrarily poorly in the worst case. And so what we created then is a fast, greedy approximation algorithm with an a priori performance guarantee and a natural convex relaxation to determine after the fact how to certify the near optimality of the result that we have. And again, because we have different objective functions, we get different results, but the modular one gives a result of about 0.63 opt, and the submodular objectives get something which is a function of alpha here, which in the case that B over K is very small, it attains the same 1 minus 1 over E that existed up here for the modular. But we also can now give an indication of what alpha is for different values of B over K ratios. And remember, B is the communication, that's the number of observations, and K is the computation, the number of potential loop closures. So again, these are numbers that would tend to be picked by the user, and you then now have a handle on what type of performance objectives and guarantees you could expect given that BK ratio. Typical result here is shown in terms of the normalized objective. This is relative to what one might expect if you had infinite resources. So of course, one is unobtainable when you have a constraint. But we have a situation where if you just sort of did random stuff, you end up with a result that's not that great. But as discussed up here, we can actually find a convex relaxation upper bound on the optimal result, which then follows this nice green curve here. And you can see that our blue result, which is the proposed algorithm, now flows up very closely to that result here. And this is a particular case where B is 150 and we're swooping across different computational budgets. And so again, as you would expect, given a certain amount of communication, if we increase the computation budget, the performance is going to asymptote up to a number that's much closer to 1 than we were getting down before. And so these are the kinds of results, and we were showing this on the Kitty data set where we're sort of simulating different robots running through the world. They have crossing paths, and as a result, they have features that they can exchange. and then develop better navigation solutions in that environment. And so these are the kinds of results that help us begin to address the questions that we talked before in terms of who should exchange from what, and essentially when. And so now we have a situation where we can begin to address through a new collaborative SLAM algorithms how to think about resource constraints within the framework of actually doing exchange, sort of exchange of information from the robots themselves. So to summarize, we have shown sort of two bodies of work here. One is thinking about a distributed, scalable, deconflicted information flowing. We've considerable robustness to sensing and accuracies. And again, we're not necessarily enforcing the alignment of the frames. And that gives us a way to work, and our algorithms work in this no align frame. We're not requiring communications required to achieve this alignment. We explain the entire pipeline that's listed up here, where we have an offline piece that's done computing the control gains for the formations, and then an online piece that involves both the perception components of navigation and the task assignment and the formation control. And we set up a bunch of different experiments that we're flying in the lab, some showing purposely creating situations where we have gridlock when we're flying in 2D, and then showing how the task reassignment up here can be used then to reconfigure the formation and actually reassign the vehicle's locations in the formations in such a way that we can now overcome the gridlock situation. The algorithms are completely scalable, running ADMM at the base station, actually compute the control gains, which determine how the vehicle should actually maneuver to get to the their locations in the formation. And again, that's done at the base station, but could be computed in distributed fashion if wanted. We have CBAA doing the distributed auctions without requiring the frame alignment exist. And so that's a consistent task assignment with the assumptions about the misalignment in the frames. In terms of the resource aware into robot loop closure, again, we have collaborative SLAM problem we've been looking at. And the key part here is embedding the resource awareness into the optimization problem. And we're no longer just thinking about exchanging data to get good performance. We're thinking about exchanging data to get good performance subject to budget constraints on both computation and communication. And we come up with fast approximation algorithms with both a priori performance guarantees, and after the fact, we can find near optimality certificates through convex relaxation. And that summarizes the work we've been looking at in the multi-agent autonomy and navigation. I look forward to your questions.